In this video, we're going to derive and show uses of the Bernoulli equation. Before we can do that, we first have to review the conservation of energy equations that we've previously derived. The first law of thermodynamics for steady uniform flow on a thermal focus with multiple inlets, multiple exits is equation 3.41. Now, we then applied that to one inlet, one exit, that special case where the mass flow rate in must equal the mass flow rate out because there's only one inlet, one exit, so we only have one mass flow rate. Then obviously we can get rid of the summation terms because there's only one inlet and one exit, and then group-like terms, and that's equation 3.42. Then we also took equation 3.42 and we manipulated that, again, steady uniform flow, one inlet, one exit, and reconfigure that to a mechanical focus, which is also called the head equation. And in the head equation, which is equation 3.47, we have the pressure head, the velocity head, and the elevation on the left and right, and then we have the what's called the pump head or the compressor head and the head loss on the far right-hand side. This is the equation that we're going to use to derive Bernoulli's equation. So let's go over some quick terms first. The first term is streamlines, and streamlines are lines that are tangent to the velocity vectors throughout a flow field. So on the bottom right-hand side, I have a cylinder. Imagine that's a cylinder going into your screen, and those are the streamlines that flow going around it. The next is irrotational flow, and irrotational is flow in which the fluid particles do not rotate. So if you look at the drawing on your left-hand side, those little stars are supposed to indicate that they're not rotating, they're staying in the same position as they go through that flow. You can see that on exterior flow, around the cylinder, that the flow is irrotational. I also put in rotational flow, just so you understand the difference. On the left-hand side, you see a picture of rotational flow. Those little arrows around those little stars are to indicate that they're rotating within the flow. And you can see on the back side of the cylinder, this is the flow of a real flow around a cylinder at high Reynolds number. And you can see that on the right-hand side, there's rotational flow, or turbulent flow on the back side, which is also rotational. Now, if we had assumed inviscid or frictionless flow, then there would be no rotational flow on the back side. Those streamlines would go all the way around and would be irrotational the entire way around. And then finally, the stagnation point. The stagnation point is a point of zero velocity, and it occurs when the fluid comes in contact with a body. And in other words, it crashes right into the front of that body. It rapidly goes to zero. The velocity goes to zero of that those fluid particles, and it does so isentropically. And this is the stagnation point on the left-hand side of the cylinder. So let's derive Bernoulli's equation, which is simply a special case of the mechanical energy equation. So let's bring that up, equation 3.47. And now we're just going to make some assumptions and tick away at it. Okay, so the first is steady flow, and we had to assume steady flow or we wouldn't be able to use this version of the mechanical energy equation anyway. The next is inviscid, no frictional effects, as I had alluded to earlier. We're going to assume that we're outside the boundary layer of the fluid, and so it's inviscid with air outside the boundary layer. There are other fluids that we could assume inviscid as well. And then adiabatic, which means there's no rate of heat transfer. So because of that, if you recall when we defined head loss was due to frictional effects, etc., and it was that thermodynamic energy that could not be converted to mechanical energy, if it's adiabatic and inviscid, that term goes to zero. Next, we assume that there's no power devices, so there's no power, there's no rate of work. So the pump head or the compressor head or turbine head, depending on which term you're using it for, is zero. And then incompressible fluid. So the density is constant in incompressible fluids. That means the density at the inlet and the density of exit are the same. So we can get rid of those subscripts and just use density in our equation. Finally, we assume that the flow is along a streamline, or in other words, it's in irrotational flow. And we're able to just clean that stuff up, rewrite equation 3.47 with all the canceled stuff out of the equation, and that gives us the head form of the Bernoulli equation, where we have pressure head, velocity head, and elevation on the left and right-hand side. So no head loss and no pump head. That's equation 3.48. Now it's this equation, if we multiply all these elements by the density and acceleration due to gravity, we get Bernoulli's equation in the pressure form. And the units, therefore, of each term is kilopascal or psi if you work in English units. And this is the most common form of the Bernoulli equation. So this is equation 3.49, and let's break down each one of these terms. So the first grouping, the pressure, is what's called the static pressure, and that's the actual pressure of the fluid or the flow. The next term with the velocity squared is what we call the dynamic pressure, and that's the pressure rise from the actual fluid motion. And then, of course, the remainder term, the third term on the left and right hand sides respectively, you should have seen before. That's hydrostatic pressure, and that's due to elevation effects. So let's look at one application of the Bernoulli equation. It's what's called a Venturi tube. And a Venturi tube is a pretty common and simple device, and you can see what's called a converging, diverging nozzle. So it's getting narrow and then widening back out, and you can see where it gets narrow at station 2, which is the throat. Because of conservation of mass, all the fluid that's going in at 1 has to come out at 3. And so in order to go through 2, it must accelerate. And so the velocity at 2 increases. You can see how those streamlines come together, and then they come back out as it diverges. So let's show you a simulation of that flow. And you can see the streamlines coming together at the throat, and you can see in the middle those fluid particles having to accelerate to make it through due to conservation of mass. So if we take the pressure form of the Bernoulli equation, we can actually determine, if we know the velocity at 2 at the throat, we can actually determine the change in pressure. And if I was just to say, hey, look, Z1 and Z2, they're at the same elevation, so those terms cancel out because density is constant, because we assumed incompressible and acceleration due to gravity is, of course, a constant. I can manipulate the equation to say that my change in pressure from 1 to 2 is equal to the density, 1/2 the density times the change in the velocity squared from 2 to 1. And that's just to show you, that's not an equation you have to use, it's just to show you that you can manipulate the Bernoulli equation as necessary. Let's look at some applications of Venturi tube, and there's hundreds of uses of Venturi tubes, but a couple common ones. If you've ever driven or worked on an old car, it had a carburetor, and that carburetor uses Venturi. And so the air comes in as you press down the accelerator, it opens the choke valve, the throttle valve. And the air comes in through the top, and as you can see, it narrows. It's therefore accelerating through the throat, labeled here as the Venturi, which lowers the pressure and hence creates a vacuum in which the fuel is actually sucked out of the float chamber and mixes with that air where it goes into your intake manifold and then eventually into your piston cylinders for combustion. Here's another application of a Venturi tube, and this is a wind tunnel. And so a wind tunnel is essentially just a gigantic Venturi where you have a motor on the backside which is drawing air in from the front side and accelerates as it goes over your model. And that's how you're able to determine and simulate, I should say, flight conditions. Let's talk about stagnation pressure. I kind of cursory went over it and said, hey, that's where the velocity, it comes to 0 rapidly and isentropically. But let's see how it could be useful. So let me draw that cylinder again. And again, it's a cylinder going into your screen. I'm not going to draw all the streamlines. I'm just going to draw that streamline that goes straight into the front and crashes right into the front of that cylinder. So if I label where I began as pressure 1, velocity 1, and elevation 1, and I'm going to label at that stagnation point the stagnation pressure, which is P0, the velocity, which is 0, and then the elevation, and which you can see that that's the same as 1, so those are equal. So if I again take the pressure form of the Bernoulli equation and say, hey, velocity at the stagnation point is 0, that's where that fluid comes to 0 isentropically. That term goes to 0, and if I realize that the elevation is the same, Z0 and Z1 are the same, then they'll just cancel out from both sides of the equation. So what I'm left with is what's called stagnation pressure, and stagnation pressure is my static pressure plus my dynamic pressure, and that's equation 3.52, which is also on your reference data card. And just a note, if the flow is irrotational, then the stagnation pressure is constant for all streamlines. It's also referred to as the total pressure. So everywhere in irrotational flow, my dynamic pressure and my static pressure should all sum up to be the same value. Here's a great example of how stagnation pressure is used in the real world. This is what's called a pedostatic system for an airplane. And so airplane has to be able to measure a couple things. how fast it's going, how fast it may be climbing, which is a vertical speed indicator, and then its altitude, how high it is off the ground, so that's an altimeter. And these three instruments are vital to flight, and so the great thing about these instruments is they use static and dynamic pressure in order to give their readings, and therefore work in the absence of electricity. It requires no electricity to run, so in a complete electrical failure in an airplane, you would still be able to measure your airspeed and your altitude and your vertical speed. So let's just look at the static port and the Venturi, the pitot itself, the pitot system. If I have air flowing past the static port and into the head of the pitot, that area, as imagined, is going to fill up that pitot tube, and I'm going to have a stagnation point right at the tip of that pitot tube, and that's going to measure the stagnation pressure. And so I'm going to label where the static port is as 1, and the entry to the pitot system as my stagnation point, 0. And if I write my stagnation pressure equation, or my total of pressure equation, equation 3.52, I can see that I can solve for the velocity or the airspeed if I know the static pressure at 1, which is what your static port reads, and my stagnation pressure, which is what the pitot tube reads. And then if I have a density, which in an airplane we assume a density, I can then back out the velocity. And that's a great example of how stagnation pressure is used in a real-world application. So if you have any questions, feel free to talk to your instructor. Make sure you work your study guide problems and get practice using these equations.